Okay, this is the lesson on de Broglie wavelengths. The first thing you want to do, there's these beautiful handouts for de Broglie matter waves, and they have all the formulas with all the units on them, and then this is also very nice. On the back side, we've got formulas. We also have a couple example problems, right? And what you should do when you get to those example problems is explain to them that that they've got these examples in their note guide. Just turn their note guide over and then they can fill it in, and they've got these two expert examples. You should work it out on the whiteboard rather than just clicking through it on the PowerPoint, because how exciting would that be, right? So this is the basic idea, right? Is that Einstein proposes that light can act as a particle. Nobody takes him seriously at all. In fact, not for quite a long time did anyone take Einstein seriously about light being a particle, because it was such a wave. But anyway, de Broglie says, gee, if light can act as a particle in a wave, maybe particles, something like an electron, can act like a wave. We know it's a particle, but maybe can act as a wave, right? And I have no idea whether, I don't think de Broglie came at it this way, but maybe he did, right? If energy is hc over lambda, right, and if energy is mc squared, right, well, momentum is m times v, right? So the energy, the momentum of a light particle would be m times c, right? That would be the momentum of it, the mass times the velocity, right? And I know what you're thinking. You're thinking light doesn't have mass because it's energy. But think again, because it's got energy and therefore it has mass, right? This is what E equals mc squared says, is that anything with energy has a mass. Not much mass, but it's got some mass, right? So all you have to do is set these guys equal, mc squared, right? Cancel one of your m's, and you've got here momentum, right? This is momentum equals h over lambda. So that is the de Broglie wave equation, is that momentum is Planck's constant over lambda, and they've got that right there, okay? And then the momentum of a particle is also mv, right? So these are two formulas that we can use, right? And then the other formula that you tend to see in association with these problems is this one where you take an accelerating voltage and you multiply it by the charge of an electron, and that turns into the electron's kinetic energy. And as long as you don't approach the speed of light, this thing's going to work. Get close to the speed of light, and there's a different calculation that we're going to learn. So anyway, you can derive this, and that's the expression. And this little picture here I got out of an IB textbook, but the notion was that if you take a nickel crystal, the nickel crystal has these regular arrangements of atoms, and those act like a diffraction grating. And so you can get the electron beams to run into the crystal, and they will do wave things. They'll interfere with each other. You'll get bright, dark, bright, dark, bright, dark patterns here, just like you get with light. So light can do this because it's a wave, acting like a wave this time, right? And electrons can do this, particles acting as waves, which is pretty cool. So anyway, that's the importance of that experiment, right? Is that this incoming electron beam here acts like waves and makes an interference pattern, which is something that only waves can do. And in fact, they have the de Broglie wavelength. So it's not pie in the sky. It is what happens. Okay. And so the first question is, what is the de Broglie wavelength of a very heavy baseball, very heavy ball? It's got a pound. Imagine that. Okay, going 40 meters per second. Holy cow. And the answer to this is just that it's ridiculously small, but let's go ahead, let's go for it, right? The momentum is m times v, so it's 0.5 times 40. That's kilograms times meters per second. That's 20 kilogram meters per second, right? So that's my momentum, right? And then I say momentum is h over lambda, so therefore lambda is h over momentum, right? Is that right? That is right. Okay, so that's going to be 6.626 e minus 34, and this is our first example. You should tell them that's your example on the back page there. Yeah. They could put their work in there. They have way more room than they need. And this is joule seconds, right, divided by 20 kilogram meters per second. And then we can calculate that. 6.626 e minus 34, right, divided by 20. And you end up with the wavelength is 3.313 times 10 to the minus 35th meters, right? Remember that a joule is a kilogram meters squared per second squared, and times seconds makes that per second cancels, right? And then kilogram meters per second squared. Oh, we're supposed to have a meter left over, aren't we? Yeah, kilogram goes away the bison. Yeah, there we go. So you end up with meters, right? That's a good thing. Now, the point of this is that this is basically a length that doesn't exist, or something like that, right? The nucleus, which is the smallest thing we can maybe even picture, is 10 to the minus 15th meters, right? Atoms are 10 to the minus 10th. And so if you were going to observe this ball, this 1 pound mass roughly going 90 miles per hour, if you were going to observe that thing acting as a particle, how would you do it? You would have to have a diffraction grating that had atoms spaced something on that order, and atoms are much farther apart. So you couldn't build an apparatus to observe this wave behavior. In theory, you could say that's a de Broglie wavelength, but it really has no meaning, right? Let's go back to this little picture here. The reason this works is that these electrons here have a wavelength that is not much smaller than the spacing between those crystals, and that wave behavior you can observe, right? But electrons have a much smaller denominator, therefore the momentum is bigger, right? Okay. But this is just ridiculous. But they'll ask you questions like this. So that's the first example. And then I spelled behavior the British way. You got, that's good, right? And then the second example is, and this is, you get into the meat of it, right? And the second example is on the bottom of the back of the note guide they have. The second example says, through what potential must you accelerate an electron so that it has a wavelength of 1 nanometer? Well, I think the thing to do here is to figure out the momentum of the electron, then the velocity, and then with the velocity we can do this, right? I think that's what we're going to do here. So momentum is equal to h over lambda, and so it's 6.626 e minus 34 joule seconds divided by 1 e minus 9 meters. And so that's 6.626 e minus 34 divided by 1 e minus 9. And we didn't need a calculator for this, did we? The momentum is 6.626 e minus 25 kilogram meters per second. And of course, that works because it's kilogram meters squared per second squared. Get rid of a second, get rid of a meter, and right. Now, the next thing we can do is we can figure out, I guess we need to know the mass of the electron, but we know that, right? So the mass of the electron is 9.11 times 10 to the minus 31st kilogram